Welcome to BKW Physics. I'm Mr. McConnelly. Today we're going to dive into the topic of modern physics. And we're just introducing this today. One of the main ideas in modern physics is a concept called the photoelectric effect. Photoelectric effect. And by the way, as we dive into modern physics, you're going to notice that many of these topics in modern physics will start to overlap possibly with things you've learned from chemistry. So a lot of you that have a chemistry background are going to see this and say, oh yeah, I already know something about this. And we might just approach it from a different angle or add to what you learned in chemistry. So I want you to think of this. There are materials and paints that when you shine light on them and then you turn the light off, they will glow in the dark. Okay? Glow in the dark t-shirts, you got glow in the dark, stickers, you got glow in the dark paints and whatnot. And they're pretty neat. Well, how do those work? And the photoelectric effect can kind of address that. Now I want you to think of this. This is a visualization to help you understand what's happening. A lot of the things that I'm going to talk about are not actually happening, but it's a good way to visualize it, and it helps you understand the principles. So I want you to think of this. Think of like a hole in the ground, and think of an electron that is trapped down in that hole. Now, I know electrons aren't trapped in the hole. See where I'm going with this? A lot of these things are they help you visualize. They're not actually how it's happening. Remember, electrons are really in orbitals around the nucleus. But we're going to think of an electron as being trapped in a hole because it helps work through the idea of it. Now, these electrons that are trapped in the hole, we'll call this one Eddie the electron. Eddie the electron is trapped in the hole, and he doesn't have much energy right now. Where does he get his energy from? Well, in the case we were just talking about, he would get his energy from incoming light. And incoming light is actually labeled, there's a word for this, it's called photons of light. That's a new word. Photons of light. So this incoming light is going to provide with Eddie the electron with some energy. And when Eddie the electron starts absorbing some of that energy, he starts getting a little more excited. It's like you just ate a candy bar. And he starts ramping back and forth in this hole because he's getting excited. He starts going back and forth. Now if Eddie were to gain enough energy, he would come up to this dotted line, and if he passes by this dotted line, he's going to escape. Okay? He's going to remove himself from the hole. This dotted line is called the work function. So we got the work function. We got photons of light coming in. They're exciting Eddie. We got the work function. If you pass the work function, in other words, if Eddie actually gets up here someplace, boom, and he escapes, he has another name. He's called a photoelectron. So you got photons of energy, light energy coming in. They excite Eddie. If he gets past the work function, boom, he escapes, and he's called a photoelectron. That's kind of the basics of this process. Now let's fill in some of the details with the equations that relate. So if you want to know how much energy, light energy is coming in, there's an equation you'll find in your reference table that says energy of a photon is equal to H times F. And that's a reference table equation. Energy of a photon is H times F. H is a constant. It's actually Planck's constant. And you look up on the front page of your reference table, and you find what that is for me. You should find it labeled as Planck's constant on the front page.
6.63 times 10 to the negative 34.
And what are the units on that? Can you find that?
Joules times seconds.
Joules times seconds, right. By the way, that was nice that I did memorize. Okay? So we got Planck's constant, and then F is the frequency of the light. Because remember, light can come in all different frequencies depending on its wavelength. So we got these different frequencies, and you times that by Planck's constant, and that is going to give you an indicator of how much energy this light has. Alright, fine. Now, this light comes down here, and it excites Eddie, but the part I want to add here is that Eddie is only excited by certain wavelengths of light. So, if you shine green light on Eddie, for example, he might sit there and go, not excited. You shine red light on Eddie, he gets all wound up and excited. Okay? So, depending on the light that hits him is going to depend how he reacts. But either way you look at it, if you're talking about how much energy he needs to escape, the equation is W naught, that means work function, is H times F naught. Now that equation, it looks almost exactly the same. It's H times F, right? It looks the same as the one I told you for the energy of a photon. But the difference is, this little naught here means it's that specific frequency that excites Eddie. Okay? It's that specific frequency. It's called the threshold frequency. And you can remember it, because that name doesn't really ring a bell for most people. You can remember it as it's that specific frequency that makes the difference for Eddie. If you want to write it down, that way your notes will be good. So, if he gets to this point, to this work function point, boom, he escapes, and he's a photoelectron. And there's actually two different equations that can gauge the energy that he has as a photoelectron. The first one would be, well, it's a simple concept. If you want to know the maximum kinetic energy that Eddie, the photoelectron, might have once he escapes and becomes a photoelectron, you could take the amount of energy he was given by the light and subtract the amount of energy it took him to escape. It's kind of like a banking statement. You know, oh, I had this much in savings, I used this much to pay the bill, how much do I have left? Okay, it's a very simple concept, you subtract it. The other way is a little more odd, or you wouldn't really think of it. It's called the stopping potential. That's the word for it, stopping potential. And it means how much energy would you have to use to actually stop the electron from escaping. Okay, it's kind of like a backwards way of thinking of it. So this electron's going to escape. Well, what if I wanted to stop it? How much would I need for energy-wise? And the equation, in that case, the kinetic energy that you would need to stop it would be V, and I don't mean velocity, I mean potential. Potential times Q, which is charge. Now the odd thing about this too, is in your reference table, it's not going to show up in the modern section, it's actually going to show up in the electricity section of your reference table, and it's written V is W over Q, and I think you might remember using it in that section, but now they just kind of rearranged it because remember W means work and energy are the same thing in physics, so they rearranged it and they used it specifically for this situation with Eddie the electron. So just to kind of summarize real quick, to go back over this. So, you have an electron. That electron is going to be excited by a certain frequency. That frequency or that energy is coming from light. So the light, the photons, is going to excite the electron. He's going to start going back and forth. Eventually, if he gains enough energy, he'll overcome the work function. Boom, he'll escape and he'll become a photoelectron. And there's two ways to gauge how much energy he has. So for today, that's physics.